That's going to be a great opening on YouTube, isn't it? Record to the cloud. So yeah, this is lecture 3, and I hope we're going to finish off the stuff we didn't get to in lecture 2, and at least start stuff that you need for next week's tutorial homework. I will click on the relevant web page and hope the network is sufficiently alive that things work. Good. Okay. So let's have a quick recap. Ask wakes up in the morning knowing absolutely nothing, except the idea of stuff that is built up from building up more complex stuff by plugging together simpler stuff, with the property that if you take it apart, it can't keep getting smaller forever. And that's why computations in Ask actually work. Computation proceeds by turning complex problems into ever simpler problems, and they can't get simpler forever, so you eventually get an answer. Okay? So here we've said numbers are built up either from 0 or by taking the successor of a number that already exists. In other words, numbers are built by counting. And we gave an example of this number, which is 4. And then we defined plus. And here are some of the words you were asking about. We start off by saying, we're defining n plus m. And when you see variables, that's words that begin with a lowercase letter. You should think of those things as could be anything. And on the left-hand side here, you get posed the problem. So you're being told, define n plus m. You're saying plus takes 2 numbers in, gives you 1 number out, and you're asked to define n plus m. So you know that n and m are numbers, but that's all you know. They could be anything. You should think of these lowercase letter variables that show it up as belonging to the devil, or at least to your customer. These are things that somebody who uses plus gets to control. So you have to be able to cope with anything. Okay? So we're trying to explain how on earth we're going to add these 2 numbers, n and m. And we start off by saying inductively n. And what that means is, I promise that as plus computes, n will get smaller. So we're saying we're going to work on the basis that the first input to plus gets smaller and smaller and smaller until we reach 0. So inductively, n doesn't do anything computationally, but it explains an important thing about why the computation makes sense. So are we good with inductively? It's a promise that something's going to get smaller, and in return for making that promise, we are allowed to use our operation recursively, but only on smaller stuff. Okay. So next we have from n, and that's from n is like saying, where's your accent from? It's saying, where did this thing come from? How was it made? Tell me more about it. Is it a spud or a lemon? And so that's the thing that tells Ask, we want to actually see where this n came from. And we get 2 cases. Either it's a lemon or a spud. So here, you see, n has been replaced with something more specific, namely 0, and now we can see we have enough information to figure out what the answer is. So we write an equation that says if the first input is 0, the answer is the second input. In the other case, we now have n replaced by successor of x. So what is this x? It's the name of the rest of the number when you take the first spud off. So if n is 7, we're in this case, and x is 6. Are we reading this fine? Fantastic. So what we're saying is, if you see a number, if we're doing 7 plus 2, then we'll see, yes, the second case matches because 7 is made with a successor, and x, the thing it's the successor of, is 6. So we carry on by doing 6 plus 2, and that gives us 8, and then we put the spud we took off back on the front to get 9. You see how we're doing? How this is going? We're writing equations that say how to make a computation step. So you read them from left to right to say how the computation should make progress. And you can see that the thing that we promised would get smaller does get smaller. We solve the 7 plus 2 problem by solving the 6 plus 2 problem, by solving the 5 plus 2 problem, and so on, down to the 0 plus 2 problem, which is dead easy because that's just 2. Are we cool? Wonderful. Yes? Okay, thank you. This is this kind of intervention we need. And yes. So what we're saying is that inductively promises that the first input will get smaller as the computation progresses. From says we're asking where n came from, how it was made. Is it 0, in which case the answer is easy, or is it a successor, in which case we get to write, this is called a pattern. You know, it's successor of something, and x is the something. So if our first input is 7, then we can recognize that 7 is a successor, and the x will stand for 6. And then we make, yes? Okay. It's amusing to be interrupted to say, can I interrupt you later? That's fine. Right. So yes, so what happens is we make progress by adding x to m and then giving the answer one more than that. So we take 1 off, we finish the calculation, we put 1 back. So you see, we keep the promise that our next step of computation starts with a smaller first input. And because things can't keep getting smaller forever, the computation will eventually finish, giving us a sensible answer. It's one thing about most programming languages don't give a damn about whether computations make any sense. And I think that's unfortunate. Anyway, what was your question? Yeah, so yes, right. So this is the thing that because essentially what we're saying is that this way of adding substitutes, as it were, the right number for the left lemon, right? We work our way down through n until we find 0, and then we replace the 0 by m and put the thing back together again. So that's one strategy for adding. It's not the only strategy for adding, it's an arbitrary choice. And you'll find that there are several different ways we could define adding. And whichever we pick, the same things will be true about adding, but the proofs will be different. Because it's really important. The strategy that implements the program is extremely influential on the way you do a proof about the program, and it can't be anything otherwise. I mean, the thing about algebra is, statements, equations that have variables in aren't just automatically true by computation because we don't know the values of the variables. So they contain computations that have got stuck because there are variables standing for unknown inputs. And in order to make the proofs happen, we have to get those computations unstuck. Okay, so yeah, we are making choices, yeah. Well, because we don't need to. I mean, we could ask for more information about M, but we know that whenever we reach 0 on the left, the answer is whatever's on the right. We don't need to work our way through whatever's on the right. And this is good news from the point of view of, if we keep the program as simple as possible, then the proofs about the program are as simple as possible. So we're avoiding unnecessary complication. Whereas you noticed in the tutorial problem that Max and Sid and Min are basically variations on the theme of comparing two numbers. And in that situation, you absolutely do have to look at both of them. Okay. We did manage to define multiplication last time out. And you can see what plus is doing is repeating successor some number of times. And what multiplication is doing is repeating addition some number of times. And I provoked Clemens into choosing to be inductive on the second input because I've done this before and I know it makes the proofs easier. But again, arbitrary choice. Yes. Sorry. Right. So,
you want to repeat the question, maybe?
So the question was, does it matter if you go from A or from B? So a couple of things about that. You need to make sure that the thing you promise is going to get smaller does get smaller. Like I just said, it doesn't matter to whether the multiplication multiplies. I just choose it that way round because I know it makes the proofs slightly easier. So that's just a bit of craftiness on my part. You'll find that if you rearrange the definition of multiplication, if you swap the inputs of this plus, or if you go inductively and take the first input apart instead of the second, that you'll still be able to prove all the things. It'll just be a little bit more complicated. So this is a bit of experience. Right, what else happened? We noticed that plus has a neutral element, which is 0. What's the neutral element? It's a thing where if you've got an operator that wants two inputs, the neutral element is the thing you feed to one input that makes the output the other. So when you add 0 to something, the answer is to something. It's the way of doing nothing. And lots of operators have a way of doing nothing. And it's useful information to notice what that is. So multiplication has a way of doing nothing. Multiplying by 1 does nothing. So we're going to be on the watch every time we build operations that have two inputs to see if we can find a way of doing nothing. That's going to be an important repeating thing, right? So part of the issue, one of the reasons I'm saying let's start mathematics again is that I'm going to try and teach you that there are way fewer ideas in mathematics than you ever thought there were. And they come up over and over again in different disguises. And if you learn to spot that it's the same old stuff, then you need to fill your head with much less crap. And that's important when you get older because you find that your head is still full of all the crap that you learned when you were a kid and you can't get any more in. I found this, in my 20s when I was foolish enough to write songs, I could never remember the words of my own songs because my head was just full of the Beatles. It proved embarrassing from time to time. I mean, in many ways. Here's my advice about poetry. Never write it down. Anyhow, so we noticed that 1 is the neutral element for times. And then we were in the business, we were about to prove that multiplication, just like addition, is associative. That's to say that it doesn't matter if you've got a bunch of things to multiply, you can just do it 2 at a time any old way, and you get the same answer, which is, good information. This is a very, very, noticing stuff that doesn't matter is always very helpful. And what we're doing here is noticing that the bracketing of multiplication doesn't matter. Okay, so I want, maybe I do want to draw a picture at this point. So that's, I'll stop sharing my screen so that it's human-sized. While I do this, can you distribute 1-minute papers? That'd be wonderful, thanks. If you've been to Marks, you might notice that you are each assigned 3 3-letter words. This is what they're for. This is a proper 1-minute paper that Fred has manufactured for me. You can help us by identifying yourself by crossing out your 3 words. They're the very first thing you get on the CS103 Marks page is it tells you what your 3 words are. So if you cross out your 3 words, then we can identify you by using optical character recognition to read the text. And if you destroy your 3 words, that means those words go missing, and then we know who you are. But in any case, please write your name and anything which occurs to you. Right. So I want to teach you an important lesson about how to prove stuff, because it is absolutely not the rocket science. If you look at the definition of plus, you can't look at the definition of plus. Well, remember when we wrote n plus m, we went inductively on n, and we took n apart. We did from n. So I'm going to draw a little picture with boxes. Goodness me, I've picked a pen that matches my shirt. And I'm going to draw a little box around the n. This is supposed to indicate that whenever you see something involving plus, it will be stuck. It will not be able to compute if its first input is stuck. And that's because the definition of plus demands to know what its first input is. So plus won't compute if we don't know what the first input is. But likewise, the way we defined multiplication, A times B, we went inductively and from on the second input. So multiplication is stuck if the second input is stuck. Now, for sectarian balance, I'll switch to a green pen. We're being asked to prove, when we get back to the computer, that A times B times C is equal to A times B times C. So, how to start? You're going to need to go inductively on something, because the computations that we're proving stuff about are defined inductively. And we've got to go with the structure of the computation to reduce a hard problem to a simpler problem. So the key to the proof is in the definition. And what we now do is we play a game called Why Is It Stcuk? And what you do is you take these templates and you layer them over the uses of the operators in the goal. So why is this multiplication stuck? Because C is stuck. Why is this multiplication stuck? Because B times C is stuck. Why is B times C stuck? Because C is stuck. You see what I'm doing? Yes? Sorry? Because times needs to know its second input. We define times to... The computation can't make any progress until we know what C is, because of the way we define times. That's nothing fundamental about multiplication. It's about our particular definition of multiplication that doesn't make any progress until it knows whether C is 0 or a successor. So what we're saying is, if we want to provoke this computation to do some work, it's C we're going to have to look at. Nothing will move until we know what C is.
Because when we defined A times B, we did a from on B, right? So we're looking at the second argument. So if we don't know what the second argument is, we don't know how this will compute. Right?
So what we're trying to do, so that what I'm trying to teach you here is that when you're trying to do these proofs, the definitions are a massive clue. And what we have here is 2 votes for C as the thing we need to hit. Okay? So I'll switch back to, okay, that's, of course, we did that totally wrong because I'm still screen sharing. So we might need, we'll take for the video, we'll take a picture of this, this piece of paper that I just wrote, and also it'll end up in the lecture notes. Okay, so you see, yeah, indeed, second input is the thing that we need to know. Okay, so let's go. I'm going to go inductively on C, hit send, and then I hit accept. So once again, I'm saying, I promise that as this proof goes along, the thing in the C position is going to get smaller. So that the explanation relies on the fact that we already know that times is associative for any C, for anything instead of C that is smaller than C. And because things can't keep getting smaller forever, that explanation eventually comes to a conclusion. Okay, so now I say from C, and I hit send. Oh, no, I can't type. No, that I should look before I leap. Better. I'm going to remove the 85s. Okay. So you see, I didn't get a case, what if C is 0? And the reason for that is that if C is 0, both sides of the equation just compute to 0. Yes? Yeah, you should always do inductively first if you're doing it at all. Yeah, it does matter. Basically, inductively should be, if you're going to do inductively, you better do it first, is the message.
More questions?
Because it's ugly. Ask chooses names it knows are unique, but they're ugly. So I just have, I don't like them, so I make them go away. I mean, it's purely fastidiousness on my part. Nothing deep. Yes? So I didn't, ask did. Now, let's read carefully. Some details that need to be there, need to be clear. this thing here is saying plus is an infix operator, which groups the L here means left. And it means plus groups to the left. And it has priority 5. The significance of 5 is just that it's priority is relative, and it's so making plus priority 5 means that plus groups more tightly than the equal sign, which makes the equations look nice. And then this thing here, infix L 6 times, says times groups to the left and has higher priority than plus. Now, I believe this is just what you're used to, right? You're used to times being higher priority than plus and grouping to the left. So all I'm saying, I'm telling ask to behave like normal. Okay, so what's happened here is that ask has chosen not to display the brackets on the one where it's grouped to the left, because we have told ask that those brackets are not actually needed. You are perfectly entitled, and I will put them in, because in this particular problem, brackets are the point. No. Okay. Now, how are we doing? We are in a situation where you can see in this step case that multiplication is ready to go. We've identified a successor in the input which we need to know in order to compute. So we're ready to compute. So your next move is to say test instead of the question mark.
Put differently, you could ask, why is it stuck? And the answer is, it isn't.
Yes. So I hit send, and the network takes its time, and some computation happens according to the rules that we started with. And I'm going to put some extra brackets in. Okay. So here's an important thing. You can see from this given what's happened here. It's in the case where C has been identified as the successor of something. So X is the name of the something. So you're told the equation C equals S of X, which means X is smaller than C. That's good news, because it means you know something about X. And also ask has substituted the equation through the goal for your convenience. So in particular, I'm just going to write a comment. So we know A times B times X, is equal to A times B times X. So that's what the inductively gives us. We know that because X is smaller than C, we're allowed to assume that the thing we're trying to prove is already true about X. So we know it's true about X, we're trying to show it for C. So that's, yes? C has been replaced with successor of X. So we know X is smaller than C, which is why we're entitled. Yeah, so that's the equation there. Yes, thanks, Fred. Okay. So now we're not home and dry by any stretch of the imagination. But if we look at the goal, we can see a couple of things. We can see here that a sub-expression on the left-hand side of the goal is something we know about. And we can see on the right-hand side of the goal that there's a big A times. So it would be progress if we could make more things look like A times something. And we know a fact that would help. So I would like to do this proof to get from the left-hand side to the right-hand side in a smaller number of steps. You see, unlike previous things, test hasn't just knocked it off. So we have to figure out how to make a more careful explanation. So the new piece of strategy that I need to teach you is to use the root rule. So Ask has things called rules, and to deploy them, you use the keyword by. And the root rule says, if you're trying to prove A equals C, or if you're trying to prove X equals Z, then you can suggest a new thing, Y, and instead prove that X equals Y and that Y equals Z. So instead, what we're saying is, instead of doing the proof in one big step, I'm going to do the proof in two smaller steps. So, okay, I say I want to go by root, and root is a function like anything else, so a complicated input needs to go in brackets, and I'm going to copy this and paste it in here, and then I'm going to juggle the brackets to the other side. Okay, and now I hit send. The tension is palpable. And you see, I get two goals. I'll put the parentheses back here. Two goals, one of which is how do you get from the left to the middle, and the other of which is how do you get from the middle to the right. And what we're hoping is that these two separate goals are easier than the one we started with. So everyone see what happened there? Yep. Right. So what I did when I chose the thing to put in the middle was I re-bracketed this sub-expression because I know that inductively these two things are equal, and I want to see more things looking like A times. So I want to get A times out further out. So that's clearly that's progress, even though it's not conclusive. Yes. Ask when we told so. Ask is very careful not to put extra brackets in that it thinks are unnecessary. Which is why when we said times groups to the left, you don't get any brackets when the times is on the left. Right, so it's choosing not to display the brackets, but I'm choosing to write them because it's the point. Yes? Yes, that's built in, that brackets have priority. Brackets are top priority. Okay, so here, yes? Well, I chose this term by rearranging the brackets. Yes. Yeah, so you can see the two lines that come after are asking me to prove that this thing, the left-hand side is equal to the root, and that the root is equal to the right-hand side. So I'm doing a two-step equality proof. If you were doing this on a piece of paper, you would write this equals that equals the other, left-hand side eventually equals right-hand side.
But it's up to you what you put in the middle, right?
Yes. Yes. I saw that the left-hand side of the equation contained a sub-expression that I know something about, because of the inductive proof. I know that it's equal to this thing. And I can look at the right-hand side and I can say that, see that out the front, there's an A times. So I know that I can get the left-hand side closer to the right-hand side if I can get A times nearer the front. So this move I know is allowed inductively, and it moves the left-hand side closer to the right-hand side. So I don't know if I'm done, but I do know that it's progress.
In general, it's usually a good idea to deploy the inductive hypothesis, right?
Yeah.
If you spot the left-hand side, then
yeah, you should be looking for opportunities to use what you know inductively. Okay, so here in the first sub-goal, I see I've got A times B left of a plus in both sides. And on the right of the plus, I've got two things that I know inductively are equal. So here, I choose to prove that two sums are equal if their components are equal. Now, that's not always a good move. You cannot prove that 7 plus 2 equals 6 plus 3 by proving that 7 is 6 and 2 is 3. That's not going to work. So unlike with things like successor, cancelling or splitting things up into the pieces is not always a good idea. But sometimes it's a good idea, and here it's a damn good idea. So the way you do it is to say under. Under is a proof strategy where you name the top operator in that has to be on both sides of the equation. And what you're saying is, I want to prove this piece by piece. I want to move under the plus. And because plus is infix, you have to name it in parentheses. Okay, we are going to get to a cliffhanger, Fred. But you might get to do your intervention. Because that's it's time to figure out how to shut up alarm. You can see that ask has just changed prove to proven in that case. Because separately, it knows A times B is A times B, because they're literally the same thing. And it knows that A times B times X grouped this way is equal to A times B times X grouped the other way, because X is smaller than C. So we're entitled to that assumption inductively. Everybody cool with what's going on? So now we've got another puzzle here. We've got A times B plus A times B times X. So we've got two A timeses being added together, and we've got one big A times on the right. So what would you do in this situation? Informally, what's the explanation? Yeah? Well, the thing is that we don't have A times at the front on the left-hand side. It's still hiding under a plus. So you look at this equation that we're trying to prove, and you might think, well, you know, yeah, that this is boring. You know, yeah, in school you would call this multiplying out, but Ask doesn't know about that. So maybe I should get a little help from my friend.
Yeah, so we see that we have A times the sum, and we might remember that that's probably A times the first bit plus A times the second bit, right? We might expect that. And if we had that, then luckily that's exactly what we need here on the left, right? If we could just do that, we would get the right thing. But Ask doesn't know this yet, because Ask only knows what you tell it, right? So if we find ourselves in this situation where we have some other fact, which would be really handy if it was true, then we could just try to prove it. So we go up before this proof because we would like to use this fact later, right? So I'm going to go up here and I'm going to prove that A times, and I guess I should do it the right way around. So A times B plus A times C is equal to A times B plus C, right? If I had this fact, then I will be done down here. So let's see. Okay, and how do we prove it? Well, again, we play why is it stuck?
First of all, why don't you try just commenting out like the goal there? Just so you see what's going on. So we comment out the sub goal. And then something an awful lot like nothing happens. You see, ask is not complaining that that goal has not been solved anymore, but neither is it saying proven, because it's still, you haven't proven the thing. So it's recognizing that this thing does the trick, but it's waiting for you to prove this before it tells you you finished the other one. So you get proven only when everything is finished. Okay, have a go, Fred.
Okay, let's play why is it stuck. So let's look at the right-hand side first, because it looks a bit simpler. So this multiplication, well, it's stuck because its right argument is unknown, right? And why is the right argument to the multiplication unknown? Well, it's stuck because the B is making the plus being stuck. So this right-hand side is stuck because we don't know what B is yet. What about the left-hand side? Well, here, this thing is stuck because we don't know what the first argument to the plus is. Right, I guess, shouldn't I put some, no. There's some implicit brackets here because times binds stronger than plus, right? Okay, so this is stuck because we don't know what this is. And why is this stuck? It's stuck because we don't know what B is. So also the left-hand side is stuck because we don't know what B is. So that suggests that we should probably do an inductively B, right?
We should be kicking off.
Yeah.
But yeah, let's get as far as from B test and then leave a cliffhanger.
Okay, so I did an inductively B, then I do a from B.
And again, we only get
Accept it.
No base case because the base case just computes. And ugly names.
Okay, and now it's not stuck anymore because these things will compute. So I'm going to say test to see how much it computes. Okay, and then I still have something to prove. But, and again, I think, yeah, maybe we shouldn't rush this.
Yeah, we shouldn't rush this.
So let's finish this on Monday. But we're not done yet, right? We still need to do some reasoning to see that these two things are actually the same.
So yeah, we're going to have to leave that as a weekend cliffhanger, but we will knock it off on Monday. All right. Have a lovely weekend, folks. Thank you so much for all of the interaction in this lecture. This is what we need.
You tell them where the box for the 1
The
minute.
box is that away for the 1 minute papers. And because you can bet the next class will want to use those doors. So please leave by these doors.
See, during last tutorial, there was this interpreter that someone's just, it was almost like an ITE for acid. You know what that is?
Yes, I do. And